This section in notes is going to cover different ways of thinking about acids and bases. We're going to go from the very strict Arrhenius definition out to the Lewis acid and base ones, and then we'll look a little bit more about how they react. We'll talk about strength, and we'll talk about concentration. So, all definitions of acids and bases are conceptual, and it's going to basically be determined about how far you want to think acids and bases exist. So the very first definition we're going to talk about is called the Arrhenius definition. This was a Swedish chemist back in 1859 to 1927, and you want to understand that this was the definition, and we didn't even know that there were electrons yet. So to just give you a kind of historical perspective, we're back in 1884, and we didn't even find out about the electron for another 13 years. So it's a pretty strict definition because we didn't really have a lot of the other understandings that we needed to. So what Arrhenius said is that an acid must produce hydrogen ions in water. That was it. And basically another way of stating is that acids have to ionize in solution. But there was no give. It had to be that way, and that's all it was. So basically here are two different examples of showing it. The bottom one was actually the more common one. Now the top one's more common, and we'll talk about why later. But basically he said that the acid must ionize. You get hydrogen ions, and you would get whatever other ions, chloride, whatever. This one up here is just another way of showing it, but it's very similar. The other thing that Arrhenius said was obviously if we have acids, we also have bases. So Arrhenius said that bases must produce hydroxide ions in water. So they must produce OH negative ones ions directly. So sodium hydroxide would break down, we would get sodium ions that we don't really care about, just sodium plus 1. And then we would have hydroxide ions, the OH negative one, which we would care about. And you would want to understand that like what we're talking about is maybe this sodium hydroxide would have been solid originally, but then what we're doing here is now, we're superscript, let me on superscript. Now we would be aqueous, and that's a really large AQ, so hopefully you don't forget it. And then this one would also be aqueous. Couple of things about Arrhenius definition. It's very restrictive. There's a lot of things that we think of as acids and bases that didn't work with the Arrhenius definition, and you have to be in water. So you can never have a dry acid, you can never have a gaseous acid. It has to be in water at all times. So we go on, and the next guys that we talk about are Bronsted and Lowry. And Bronsted and Lowry are a Danish chemist and an English chemist that work together. And so you can see this. Now we're in 1923, so a good number of years have passed. And what they did is they made the definition a little more general. So we do that because then we can apply it to more chemicals, and it seemed to fit it a little better. I would say out of the three, this one's my favorite because I just think it's the most appropriate. Arrhenius is a little too strict. The Lewis acid is a little too, for me, wide. This one seems to be the best. So what they said is they changed it a little bit, and they said that an acid is a proton donor. And what you need to realize is that a proton donor means it's just one proton and 0 electrons. You need to understand that that equals a hydrogen ion or an H positive 1. So like they basically kind of just renamed it, but they were saying the same thing. Another thing that Bronsted and Lowry talked about is they talked about the idea that typically a hydronium ion will actually react with water. So you want to think of like this guy, the hydronium ion is aqueous, and then it's going to react with water that is a liquid, and it's going to form a hydronium ion, which would be aqueous. So what you'll see is sometimes people will refer to it as the hydrogen ion. Sometimes they'll refer to it as the hydronium ion. And honestly, it's just the same thing. They also talked about the fact that there are these things called monoprotic, diprotic, triprotic acids. So a monoprotic acid only has one acidic hydrogen. So hydrochloric acid, there's one hydrogen that's acidic. A diprotic acid has 2 hydrogens that are acidic. So you can see here we have H2SO4. And then triprotic is an acid that has 3 acidic hydrogens. One thing you want to kind of understand is not every hydrogen is acidic. So an example of that would be acetic acid. So it's commonly written as HC, 2H3O2. This is considered a monoprotic. There's only one hydrogen that's acidic, and it's that first one out front. So that hydrogen is acidic. So not every hydrogen that you see in the world is acidic, so you have to be careful. The diprotic and the triprotic lose hydrogens in step. So over here, this is just showing you sulfuric acid losing protons in steps. So you have H2SO4 reacts with water, you get a hydronium ion, and then you get a bisulfate ion, and then that bisulfate ion reacts with water again. Now you get another hydronium ion, and now you get sulfate. So there were two hydrogens that reacted, and we ended up with, that's why it's called a diprotic. All right, next one is that a base is a proton acceptor. So the proton acceptor just means that the acid is losing a proton, so the base has to accept it. Couple of things about Bronsted-Lowry. Because you're only talking about the protons, you don't have to have aqueous anymore. And one thing you want to understand is that you have to have an acid and a base. So if something's going to act like an acid, then you have to have something that acts like a base. It's just kind of like you have to have them both for them to happen. There are some chemicals that can be either an acid or a base, and those are called amphoterics. So examples of things that are amphoteric is amino acids, so you should all know that from bio. Water can be amphoteric. Hydrogen carbonate, which is HCO3, and then a negative 1 charge. And then hydrogen sulfate is HSO4, negative 1 charge. So those have the capability of either being an acid or a base. Last thing is the Lewis definition. The Lewis definition is just an expansion. So basically it focused on bonding as opposed to even like what's being transmitted. So a lot of things really are considered acids and bases with the Lewis definition. The Lewis definition says that acids will donate a proton, they'll become a conjugate base, and they accept an electron pair so that they form a bond. So the emphasis is really on this electron pair, the electron pair and the covalent bond. So it's just a different way of looking at it. Okay, so we're going to move on to the next slide. Same thing, very similar, but this one, the bases will accept the proton. They become a conjugate acid, and what happens is they donate an electron pair, and they form a covalent bond. So again, it's that focus on the bonding and not the like what's being transferred. Okay, so one thing you may have noticed was they talked about conjugate acids and conjugate bases. What it deals with is when you start something, you're one type of chemical, and then you become another type of chemical. So if you start out as an acid, then you become the conjugate base. And if you start out as a base, you become a conjugate acid. And it's pretty simple when we do them. What we do here is, let me get something to write with. Okay, so what you have to do is you have to find who matches who. So ammonia is similar to NH4, and that water is similar to OH. So what you have to look at is what happened between the two. So between the two, we have NH3 and then we have NH4 plus 1. So what you want to realize is that between NH3 and NH4 plus, we gained an H plus 1 ion. What that means is that the ammonia is the acid. No, sorry. It means it was a base. And then that means this guy over here is called our conjugate acid. So it's kind of just basically like what's happening. So if you start out as a base, then you become a conjugate acid. Same thing if we look at water and we go to OH minus. What happened is we have 2 hydrogens and now we lost one. We only have 1. So what's happening is we lost an H plus 1 ion. And what that means is that the water started out as an acid, and then over here is considered the conjugate base. So you want to see that whatever you start out as, you end up being the other thing on the other side. Okay, we'll do one more together. And again, what you should notice is who goes with who. So we have like HF going with F, and we have H2O going with H3O plus. And then if we do this, what we want to realize is from HF to F, what happened was we lost an H plus 1 ion. And what that means is that HF is the acid, and that means that F minus is the conjugate base. And then if you look from water to H3O plus, we have 2 hydrogens and now we have 3. So what that means is that we gained an H plus 1 ion. And what that means is that water is the base and H3O plus is the conjugate acid. So what you want to realize is just understand that like you're switching roles from one thing to the other, and keep in mind that one thing has to be a base and one thing has to be an acid. So take a minute, pause the notes. This is not in your notes, just write it down like on the side or something, and try it, and then see if you can figure out who's what. And then what'll happen in like 10, 20 seconds, I'll put the answers up. Okay, so in this one, what you should get is that HSO4 is the acid, and that SO4 minus 1 is the conjugate base, and that ammonium is the base, and then ammonium is the conjugate acid. So make sure that you made the connections. You should have seen that this one goes to this guy, and that this one goes to this guy, and you should see what's changing between the two. All right, and then the last thing for this section of notes is you want to realize that there is a difference between the strength of an acid and the concentration. So the strength of the acid refers to how many things are ionized. So when we say ionized, what we mean is like HCl becomes H plus 1 and Cl minus 1. So if you're a strong acid, then you completely ionize. So these are the acids that are considered strong because they ionize. If you're a strong acid, then you are a strong electrolyte. Strong bases also do 100% dissociation. So like lithium hydroxide, sodium hydroxide, any of the alkali metal hydroxides, and then calcium, strontium, and barium hydroxide as well. So what that looks like for a base, if it lets me type, is, let's see if it'll go down here. I don't know. All right, so if we do this one, like lithium hydroxide would break down, and you would get a lithium ion, which is aqueous, and you would get a hydroxide ion, which is aqueous. And that would be a -1. I don't know why it's not showing. There we go, -1. So you just want to realize that strength is all about do you ionize or not. And if you look at this picture, what you want to see is look at the strong and look at the weak. And notice how the strongs are all pluses and minuses, pluses and minuses, pluses and minuses. Look at how the weak is mostly the acid kept together. And then the last thing for this section is weak acids are not really ionized, where they have less than 5% ionized. So they have some of the ions, they have a little bit of the ions, but most of it is just the molecular form of the acid or base. These are considered weak electrolytes as opposed to strong. And then what you want to remember, concentration is all about molarity. So if you're talking concentration, you're talking molarity, which we should all remember is your moles of solute divided by liters of solution. And if you look here, there's a difference between being concentrated and dilute. That's the actual like amount of your acid. But that's different than being strong and weak.